first to 50 episode. Here we have a lesson on theoretical mechanics. And in theoretical mechanics, we will be taking a look at vibrations and waves, or more specifically, mechanical vibrations and mechanical waves, alright? So what is so special about this mechanical with vibrations and waves? Now, for some of you might have already learned waves, waves on water and electromagnetic waves. But the point of mechanical waves is that we would not be looking into other types of waves like electromagnetic waves, but we do have things like your water waves and all, okay? So that will be what we will be having for this lesson, right? So in this lesson, let's start from the basics. So what kind of things are the basics? Now, one of the first formulas you could learn, or one of the first things you could learn, would be either a spring or a pendulum. So how about let's start from a spring first, alright? What's so special about a spring? Now, normally in your questions that you have, you will see a spring that is locked onto a wall and is pulling something. Or you can give this thing a bit more force to stretch the spring or to compress the spring. So those are what you can do with the spring. And how do you calculate the amount of force you have in that spring? So let's just say you have your wall over here, you have your floor, and you have this spring. Alright, so this spring is pulling a mass. And let's say at first at this spot over here is its original length, alright? So originally the spring is this long. But now you have a force on the mass that pulls the spring this much. So how do you calculate the force you have over here? Whoops, X and not K, sorry. So this is F is equal to negative Kx, alright? With K being your spring constant, which can vary from spring to spring. So K, you have to test it out by yourself. X, you can just measure it. While negative you have to be aware, since this negative will be the force by the spring on the mass. So when you have a force on the mass trying to pull it away from the spring will want to exert a force to pull itself back to original position. While instead, if you compress it, then your so-called displacement will be negative as it tries to push itself back and pushing against the mass. Alright? So this is what you know as the Hooke's law, right? Now, Hooke's law, F equals negative Kx. Do you know of anything else that also has F equals something times something? Well, that would be the more basic version of your basic, which is F equals ma. So yes, of course, you can link these two together, but exactly how? So how about let's change your acceleration first. If you have learned differentiation, it would be much simpler since you would know acceleration is actually the second derivative of the displacement that you have. Well, it is derivative with respect to your time, alright? So this is how you can change your Newton's second law. So since we both have F equals something, we can equate them together. But you might be wondering, what is so special about equating them together? Later you'll see what exactly can you get. Now how about let's move this Kx to the left side. So you have plus Kx and this is equal to 0. So this m of course being the mass, whatever acceleration it has, alright? So how about let's divide m on both sides. So you might be wondering, what is the importance of this? it might just look like some weird second derivative plus a coefficient times an x that is equal to 0. And if you have not learned differential equations, then this could be rather difficult to understand, since actually in differential equations, here you should be able to solve what x is. Alright, so if you have learned a little bit of differentiation, you would probably know of something that x, you differentiate it twice, it can cancel out itself. And what could that something be? Well, of course, you can just directly calculate it in this form, or you can also change your k over m into an omega square, alright? So, those, you can just convert it into omega square. Well, this will come into play later, alright? So, what would be your x over here? Now, there are 3 possible answers you can get for your x, or maybe even more. But those, it could be like a lot more complicated, or a combination of a lot of things. But now, the x that we'll be looking at will be more simpler forms, which, the first one, it could be, now of course, since each of them, they could all have a coefficient in front of them. Since the coefficient doesn't do anything, but it stays constant throughout both of your x's. So yeah, you can have a coefficient over there. Now you can have sine, right? Since sine and a second derivative of sine will be negative sine. So if you just have sine x, that wouldn't be right, since you have an omega square here. But second derivative, that means you will have omega inside here. So a sine omega x, and then you can plus, let's say, b or something, since this wouldn't really matter. So wait, whoops, sorry, x is not in terms of x is in terms of t. Oops, sorry about that. Alright, so you have to be aware x is a function of t, since x, and you have a function of t. Right, so this is one of the possible answers that you can get. Now, when you think of sine, what else do you think of? Of course, you will think of cosine. So cosine, it would pretty much be the same. Now, what would be this third possible answer be? So what differentiates will get itself? The other answer you probably would think of is your exponential, since e to the power of x differentiates to e to the power of x. But for your exponential, it would be rather a bit more tricky, alright? Since you have a, same thing, so e to the power of. Now, omega t, but if you just have omega t, it will still be itself, but it adds onto itself. So you need something to change its sign, right? But if you just add a negative, 2 of the negatives will become a positive. So you need 2 of something to become a negative. And that is why, if you have learned complex variables, you would know what to do here, since you can just put I. Since differentiated twice, you have I squared, which makes it a negative, which makes it able to cancel out with the other term. Alright? So then of course you can have like whatever plus b over here, whatever, it's up to you. So these are 3 of your possible forms for x, alright? So now, what is so special about all 3 of these forms? Okay, so of course here you can just add a plus b, but alright. So these 3 forms, of course the last one seems more complicated. It depends on what kind of surface you use. Since if you have, like, let's say another negative in front, then you'll have more of a damping kind of situation, which it just slowly stops. So we won't be taking the last one for now. Of course, we will explain more about it in the future since it's more complicated. the first two cases are much easier to understand, isn't it? Since you would probably already have learned sine and cosine graphs. So sine and cosine graphs, or sinusoidal and cosinusoidal graphs, whatever you like to call them, the thing about them is it keeps repeating, right? So if it keeps repeating, what does it mean for your scenario over here? That means whatever energy you have inside is conserved. You do not have friction between your mass and the floor, so it does not slowly come to a stop. It just keeps vibrating about, right? Okay, so now what would be the next thing you think of? You might be thinking of, what is A? What is omega? What is B, right? Okay, so we'll be answering that. Now, A. If you have learned sine and cosine graphs, the maximum is 1. The minimum is -1. But wait, if the maximum is 1 and minimum is -1, you pull this from like 2 meters away. Is that not possible anymore? No, it's still possible, which is why we have A. So A is your amplitude. So this is just how far it goes, alright? So now that problem solved, A is your amplitude, and what is omega? So omega here is actually something known as your angular frequency. But what's so special about that angular frequency? So angular frequency, it is like frequency, but in angles. Since let's say you have something that occurs a certain number of times, or let's just say, for example, your sine graph. If a sine graph within that period of time, or let's say within a second normally, unless you want to change your frequency into a different period of time, whatever. So let's say within 1 second, it just repeats once. So when it only occurs once, your frequency will just be 1 times per second, right? So 1 times per second, but that is the normal frequency that you're going to have. But for angular, since this is now angular, that means you would have your normal frequency multiplied by 2 pi, alright? So it is pretty much like whatever you learned before, for example, angular momentum, angular velocity. They're pretty similar. You take the original, most of the time, you just multiply by a 2 pi. It depends on what you're looking at though. So you have to be aware. Or for angular, you're just thinking in terms of angles, right? Since you do have sine and cosine, where inside here is an angle, right? So how about B? Or you might use something else to represent it here, but actually any constant works since you just need to write it clearly. So B, what would this thing be called? This would actually be an initial phase. Why do we need an initial phase? What is a phase? Right, so let's start from the beginning. What is a phase? So a phase, let's say you just have 1 cycle of this. So when you begin the next cycle, that starts your second phase, alright? So you pretty much just have 1 period of this entire thing you have, and when it starts repeating, that starts another phase, alright? So now, let's say initial phase. Of course, if you look at this sine graph, it seems that it just starts from 0. So what does it mean to start from 0? That means your mass just starts from 0 first. And if it increases, that means your time starts here and it moves outwards first. So that is what's happening in this graph. But what if you want it to start from outside here first? Alright? if you wanted to start from outside first and move inside, that means you would need to start from 1. Well, I mean not really 1, but it's just a peak of the sine graph that you have. But if you don't have this part, t is just 0, so you can't change that. So that is why when you add on another angle, you have something called your initial phase, which is where it starts from. Of course, initial phase, you can keep on changing, since every time you add 2 pi, it just restarts its phase, alright? So, that is pretty much it for what you have for sine and cosine. Well, depending on the case, you have to really be aware too that sine and cosine, although the graphs are pretty similar, they do have a little phase difference, alright? So, that will be pretty much all we have in this lesson. Alright, just starting off with the basics, solving a differential equation with these 3 different solutions. We've explained the first 2. We'll leave the last for some future lessons to explain more in details. Alright, so I hope for this lesson you're clear of pretty much everything so far. Alright, so I'll be ending this lesson here, and thank you for your watching.